Hello. Hello.
Yes, sir.
Okay. Good. So let's start today's class. Most likely today will be the last class of the semester. So yeah. So before I start, any doubts, any questions? Okay. So if there's no doubts and questions, then that's excellent. So can you see my screen? So in the last class, I was talking about matching. Okay. So what is the problem? So you have been given what? A graph G, and your goal is to find say maximum matching. What is the maximum matching? It's a kind of the largest matching that you can think of, or largest is possible rather. So do you have any? So of course, a special case is asking whether a special case is like, does there exist a matching of size greater than or equal to k? So that is a kind of a question that is like the Boolean version of the decision version of this question. So I left it to you guys to think about it. So did you guys manage to think anything about how to go about working on that? Ayonabo? Hello? I cannot hear you. Okay, I cannot hear you just. Siddhartha De?
Yes, sir.
Yeah. Did you guys think about this problem?
No,
Oh,
sir.
you were not there in last class, right? What happened? Excellent. Siddhartha De, why did you mute yourself?
Yes, sir. I am listening.
Did you think about this problem? Or you are not there last class, therefore you did not think about this problem?
Oh, sir, I have not think.
Were you there in the last class? You're not, right?
Yes, sir. I was not in last class.
Okay.
I was.
Were you there in the class before that?
Yes, sir. Yes, sir.
You were there not in last class, but you did not even think about try to make up for that class or try to understand what is there in the class. That's very good. I don't know why you are here in today's class. Anyway, so the people who are there in the last class, did you guys do you want to take a shot at this? Maybe Akshay, Thomas, Devashree, or Subimoy, Pradeep. Do you guys want to take a shot at this?
Sir, like I could not think of any.
Okay, so if I give you this problem, how will you go about thinking? Let's start with that. I mean, I just want you guys to think about it in some direction, even if you cannot finish it.
So, first, I was thinking that if it is a bipartite graph, if we can verify that, then
Yeah.
we can check like let's say using the Hall's theorem, but then the number of subsets would be exponential.
Yeah, that is by applying Hall's theorem. So you can
I
check.
cannot verify that. Like, that would be
Yes.
exponential in time.
Yeah.
Uh.
And also that is only for perfect matching. I mean, this is only when you can match all of them, not just for any general case. But that
Okay,
will
but-
also be exponential.
Oh, I remember the last classes was we are
Yeah.
discussing
But yeah,
perfect
I'm
match.
just telling you
Okay, okay, yeah.
that is also for the exponential, and it's for perfect match.
And
Okay.
another thing, approach might be to start with any age taking as a matching and see if we can keep extending.
Yeah. Okay.
it.
So how do you grow about
But-
that? Yeah.
Like in some proofs of graph theory uses the augmenting path argument, but I do not know how to translate that into an algorithm. Like how to efficiently do that.
Okay. So what is an augmenting path?
So basically, given any
Yeah. So if I give you a graph, okay, so like a graph like this. Okay. Say, yeah. So I tell you that, okay, so look at this one. I have chosen this. So this one and this one. This is my match. Now question is that, is this the maximum matching? Now this is a matching, that's no doubt about that. Now if it is not a maximum matching, what does it mean? There can be some other matching. So
Yes,
the- yeah, sorry. Yeah, who was it? Akshay, right?
No, sir, it was.
Sorry, I did not hear. Who was it?
So it was not me.
Oh, okay. So who was it trying to say something?
Sir, I was saying that it is not the maximum.
It is not the maximum matching.
Yes.
So let's see if somebody gives you. So what is the maximum matching? So is there some other matching which is bigger than this?
Yes, sir.
Okay. So how do you see a bigger matching? What is a bigger matching, say?
Sir, can you name the vertices? Otherwise, it is.
So say 1, 2, 3, 4, 5, 6, 7.
1, 2, 5, 7, and 3, 4.
Okay. 1, 2, 5, 7, and 3, 4.
3, 4.
Now there are two matchings, right? One is this our original one, and other one is this blue Wrigley matching. So what happens if I look at these two matchings together? What do you see? See, I have given you one matching M1. So this is a subset of the H set. I have given you M2, which is a subset of the H set. Now, how will you look at these two matchings? Now, there are basically three kind of possibilities. Okay. Number one, there are some edges that are in M1 and M2. That's possible. Number two, if you look at these matchings and look at the ones that have kind of not there, okay, you can prove that if I look at M1 union M2, say minus all the matchings that are in the all the edges that are common, they will split into two kind of things. Number one, they will form either triangle circles, either circles of this form, circles like this, where you will have one from M1, one from M2, and one from M1, and one from M2, and so on. Or you can have edges like this, Okay. Sorry. Or you can edges like this, right? These are these kind of possibilities are there. So this, if I just look at the union of these two, and this is kind of a very easy observation to make. This is not a hard observation at all. Intuitively, it is kind of very clear that what will happen. Okay, there will be some edges that are not there in either of them, some edges that are there in both of them, and for other things, it would be it will alternate, right? Because of course, if I have this edge in M1, then how can I have this one edge in M1? That is not possible by definition. So I can have this edge, and then I have some other edge M2, then M1, then again M2, and so on. Or I can have say M1, M2, M1, M2, M1, M2, and then I just stop. So this is the two possibilities. Any doubts about that? Okay. So, assuming that you guys all understood this part of the line. So note that here, if you look at here, okay, this edges that are there in M1 are also there in M2. So this doesn't contribute anything more. So if I have, say, if I have that the size of M2 is more than size of M1, strictly more than, then which one do you think has to be there? Then which of the cases has to be there? Basically, what I mean is that in the first case, the number of edges in M1 and number of cases in M2 are same. This also, you can see the number of cases in M1 and number of cases of M2 is same. Here also, although I have drawn it in this way that there's a 3 M1s and 3 M2s, but you can see that there can also be another case when I can have 4 M2s and 3 M1s kind of stuff, right? So they are like alternating, but since these are not necessarily a cycle, so they are the line which alternates. Now, what it means is that here in this kind of a situation, if I don't take, if I remove these edges and instead pick these edges, I would have increased the size by 1. So this kind of stuffs are what are known as augmenting paths. So basically, what I'm saying is that if I have to solve this problem, right? One thing is try to solve it exponentially using some control. The other one, this is also something that we have talked about in our previous classes, is that to study the object that we are supposed to find. In this case, a matching. And if I produce a matching and somebody else produces another matching, or if I look at the maximum matching or whatever, how will these two matchings look like? And basically, the way in which it will happen is this, right? They have to be something like this. Note that it can also happen that they can have a single path. This can also be an augmenting path. Because this one has one, this one, and none, and nothing on this other side. Which means that this path can also be picked up by the, if it has not been picked up by the blue things, right? So, in other words, if I find a maximum matching, if I have any matching, okay. So if I start with a matching, any matching, okay, then it means that if, say, matching M1, say, if M1 is not maximum, then what can I say? That means there exists a match, there is another matching, there exists a matching M2, which I don't know, which M2 strictly bigger than M1, which means there exists a what? A alternating path,
Same path.
hmm?
Okay, all right.
Augmenting path, alternating path, right? Now, what is the speciality of this vertex? Can you say what is the speciality of this vertex in the inside the blue matching, inside the blue matching M1? What are these two vertices doing? What are these two vertices? So in the M1, which is blue vertex, this one has been matched to this, right? This one has been matched to this. This one has been matched to this. This one has been matched to this. What has this been matched to? Anything?
Nothing. They are the unmatched vertices.
They are the unmatched vertex, right? So in other words, that means that there exists a path between two unmatched vertices. Two unmatched vertices such that it is an augmenting path or alternating path, whatever you want to call it. Okay, so all that we need is to find out a path between two unmatched vertices that alternates between a matched and unmatched vertex. It starts with an unmatched vertex and then alternates. Now that's it. If you can find one, if you can find such a path, then what happens? I start with M1, find such a path, right? Let's let the path be P. If you can think in the kind of this notations of Boolean algebra, if I take this M1 and XOR with the path P, meaning I have all the other things are same. Sorry, I'm not XOR actually. Sorry, I mean I kind of XOR with the path P, meaning these edges. So initially I had these edges. I will now throw them out and I keep this edges. Now because it's an between two unmatched vertices, note that no other vertices which was matched earlier has become unmatched. So that means this one, if I call this one as M2, M2 is strictly more than M1. And that's it. That's all that is there in the algorithm. You start from a unmatched for any matching, find an augmenting path between two unmatched vertices, and add that one to my matching. My matching will increase by at least one. Continue this. How many times can you continue this? So let's try to understand this time complexity. So is the algorithm clear?
Hello, sir.
Yeah.
So I had the query regarding how to find the augmenting path. Is
Yes.
it the brute force approach seems to be just taking all the unmatched vertices and taking some BFS of some sort?
Yeah. So that is good enough for now. Let's start with that.
Okay. Okay.
Let's start with that. Okay. You can take every pairwise unmatched vertices, that can be n square of them are there, all total. And between any two of them, if you do a BFS kind of stuff like that, you should be able to find a path.
Yes. Yes.
Think about it, how to exactly write it down properly.
Yes.
Okay, but you can do it.
Okay.
Exactly, this BFS or DFS kind of technique will do it.
Okay. Okay.
So time to find augmenting path, at least for now, this can be order n squared times e plus v, right? E plus n or m plus n, because sorry, because n squared, because there is the all for all pairs, and I have to look at, I have to run the BFS, which means order of n plus n, and I have to run this whole thing. So number of times I update a matching, this is not more than order n, right? Because how can there be more than order n size match? And every time I update, I increase matching. So the total time is equals to order. So if you can think of m to be n squared, so this is order m to the power 5. So that means in order n to the power 5 or in polynomial time, you can find the matching. It is very easy. The reason I had asked you guys to think about it is exactly because of this. Coming up with a polynomial time algorithm is actually quite trivial here. All you have to do, and this is not just for the case of this problem, okay? So, the goal of this algorithm course, for people who have attended this course at least, was that there are certain ways of approaching a problem, and these ways are what we want to deal with, right? Of course, if I want to kind of quickly recap of whatever things that we have done in this course, okay, you can start with an algorithm, and you can start with the greedy algorithm, or which you can mostly of the time becomes a heuristic algorithm. What's the problem with this? Okay, the easy part is that this is an easy algorithm to do. What is the hard part? Prove correctness. It is not easy to prove correctness, and most of the time, if it is correct, many of the time it is not, and in that case you have to give other empirical results or something like that, and they are not very easy to produce. But this is the most natural way people always approach an algorithm, greedy algorithm. That's it. This is where I think our algorithm course should have started, because this is something that everybody knows. The next thing to do was recursion. This is something that I asked you guys a few times. Recursion or recursive algorithm. Think about recursive algorithm in some way. How to use others to solve the bigger problem. Or maybe this is not the right way to write. How to, or split the problem into smaller problems. Now, this is something that we have spent quite some time on this whole thing, and basically it includes things like divide and conquer and the dynamic programming algorithms. Basic idea is nothing but think recursively. So this was the first thing that people who have attended this course should be keeping in their mind. Recursive algorithm, think recursively. Third point, okay, exact exponential time algorithm. Okay, this is not very fun, but if you cannot come up with a good example problem, then maybe you can't do an exponential time algorithm. They can be they are again not too hard. These are easy, and they can also, but they are slow, right? Something similar to in this direction is, can you prove this one in NP? This might help you to think about how to solve the problem in NP. Once you solve a problem in NP, this helps you to also this particular, or maybe I should take this one as a separate thing. Okay, so that will be a fourth thing. So you try to, once you have this exponential time algorithm, try to push it down. So that, okay, I cannot solve the problem, but can I check whether a solution is correct or wrong? And if you can do that, you can solve it in NP. This gives you two parts. Number one is that reduction to other well-studied problems. Now, this is something that we have spent quite some time recently, the SAT, ILP, and so on and so forth. And right here is the other thing, which is like you have to convince people that can you do it better or not. Okay, so this would be, right, is it NP complete? Now this is the opposite direction. So this first one is helping you to solve the problem using some hard problems. This one is going to say that, okay, this problem is as hard as hard problems. So I don't expect me to solve it quickly. And the fifth thing, now this is not that this is the last thing that I taught, but it has been there earlier also, is that many times when you want to solve something faster, just because it is, so if not NP complete, then you can try to solve it. Maybe there is a more cleverer algorithm to solve it. Okay? And the one way of getting to solving it is actually try to understand or study the object that we want to output. Now, you have seen this one also in something like you have seen it also in something like the minimum spanning tree kind of problem, where we had studied it in that way only, that what happens in a minimum spanning tree. The very fact that the minimum weighted edge is in the spanning tree helped us to pick that one up. And basically that is how we kind of developed the Kruskal's algorithm or the Prim's algorithm, both in some sense, right? Similarly here, just trying to understand how the matchings work, we are able to do it. So in this course, if you guys can, please for yourself, try to understand these objects, a recursive algorithm, exact exponential time algorithm, in whether something is the NP or NP complete, and how to approach it. So this is the basic, I mean, this one is something that we already knew in some sense. The rest of them is how one approaches algorithms, not only in theory, but also in practice. This is exactly how one is expected to tackle algorithms. Okay, so this is what is important to learn. This is what we call as algorithmic thinking. Think in the algorithmic way, not just, okay, let's do it in some way. That would most likely, most often than not, lead to just a greedy algorithm. But instead of thinking about greedily, either think recursively or think by reduction or think by trying to analyze the final product. So these are the three basic ideas that are there. Okay. Yeah.
Sir, can you give us some examples of exact polynomial algorithms that we have discussed in class? I think TSP and the garage cell problem that were in the assignment, are they?
Yeah, we have not done exact polynomial that much, but you guys have come up with exact polynomial. For example, I mean, this one that you told today, right? Matching problem, right?
Yes, the whole theorem one, right?
Or defining the vertex cover,
Yeah,
right?
yeah.
All the algorithms that are in NP and particularly NP complete, they can be done in exponential time. Okay. Now
Yeah.
I must say here, don't think that the exponential is the worst. Okay. There are algorithms that are way beyond exponential, double exponential, triple exponential, even not even way above that. And you say, oh, who uses it? Actually, many of them are used. You will be shocked you will be really shocked, because many of these robotics people who have all these various learning algorithms, various algorithms that goes into robotics, various verification problems, many of them are in a complexity space which is way beyond exponential. Okay, so if you can get something in exponential, that is many times great. Okay, so I mean, so if I kind of draw this picture over here, so there's P, there is NP. NP is actually within the class of what we call as X. X part the exponential time algorithm. And then the set of other algorithms that we can solve, that is called this RE, recursively enumerable or computationally enumerable, or recursive also. These are like way beyond that. And then there are double exponential, triple exponential, then all of these things are there. Okay, sharp P, this thing, that thing. There are enough number of problems that are there in this area. You could be shocked too. So in fact, almost all the problems that people are interested in for most of real life applications are either in NP or X or beyond X. In P, very few algorithms exist. Okay. Now, if you want to learn more about this set of problems, I must say that you have to look into areas like logic, where things are done. Then there is a whole area called exact algorithms. Then
Sir, on this topic,
yeah.
I plan to ask you in person if possible, but this is the last class. Would you be taking the computational complexity course in either of the next 2 semesters?
I plan to. Yeah.
Okay.
Yeah. So that's the other thing. This of the complexity theory. There also you kind of would learn a little bit on this things. Okay. So so in this last, so whatever I have done so far, okay, all of it will be there in the exam material, exam stuff for you.
So including the recursion and before myths and everything.
Oh, everything. Yeah, of course. See, algorithms is not like doing a course or something, right? It is about trying to attack a problem. And now I am not going to tell, I mean, almost no problem will say that, okay, do it using this technique. Your job to find out which will work. So you have some amount of intuition that will have from which you will be able to understand whether I should do a recursion or whether I should do a kind of a maybe divide and conquer kind of stuff like that, or maybe may not be at all possible. Maybe it's NP complete, something like that. Okay. Yeah. Good. So in the next class thing that yeah, so I know there will be the other course that happens after that is the advanced algorithms. Now I'm just going to say a little bit on this, what all things will be done here, and they are all related to, maybe this is something I done in the last class, I forgot actually, but this is all most
Sir,
of
I
yeah.
don't think there is an advanced algorithm course in our curriculum, at least not in the course research.
There is something, there is a not advanced or
There is
something.
randomize and approx. Is
Oh, okay, that
written.
randomization approach. Okay, whatever.
Yeah.
Yeah, so the randomization approach. Yeah. So what all things do you do here? So I will try to explain you how you approach this whole thing using using the problem of vertex cover. Okay. Now, how do you do vertex cover problem? Okay. So you guys remember the vertex cover problem, DC? So you have been given a G and a K, and the question is that does there exist a vertex cover of size less than or equal to K? How do you approach it? Now, okay, let me tell you certain facts that we have done already. Vertex cover is NP complete. We know that. Vertex cover is has an exponential time algorithm. That also is something that we have seen. What all things? Vertex cover, of course, since it is NP complete, can be reduced to ILP and so on. Now, do you guys remember how do you solve the vertex cover in ILP? So you remember, so it was like I have this graph and I have this x size, which will basically represent 0 or 1 depending on whether the vertex Vi is in VC or not. And I would want to minimize summation of xi. Okay. Minimize summation of xi, I equals to 1 to n, right? Such that what? Of course, one of them is that the xi's are either 0 or 1. And I want to say that every edge is, just 1 second. Hello. Yeah, hello, sorry. So for all edges E1, E2 in this edge set, what do I know? That the XE1 plus XE2, this must be more than or equal to 1. So it is at least one of the edges, one of the vertices at the end has been picked up. So this is an ILP. You can go and verify it, that this is the ILP of the vertex cover. Now from here spins two interesting problems. Now these are the problems that one of it we have discussed to some level. So what is the, so there are, so I will just, let me talk about two different approaches that I can think of. Yeah. Number one, you guys want to take a shot at it?
So one of possible ways to go via a standard ILP solver that is available,
Yes,
and
that is
the
one
other
thing.
is solving it in LP and then
Yes.
assigning soft values. or
Yes, so
some
relaxed,
social mechanism.
yes, relaxed LP, relaxed ILP. So that means you replace this particular thing with xi are say between 0 and 1 and use the value of xi to randomly pick vertex vi. And then you kind of argue, okay, that with, if I do it with this may, then with high probability every vertex will be picked or every edge is covered. With high probability every or almost all edges will be covered. You prove it, you prove the correctness or actually it's not the correctness, you kind of, I will say they analyze the result, the output, how good the output is using, basically these are called probability bounds. So like if I pick this one with probability vi, with probability xi, then what is the probability that a particular edge is not picked, and take an union bound on that and so on and so forth, and you will have some idea. Okay, so you can give a mathematically correct way of doing it. So this is one approach, something similar to this. This is what we call as randomized algorithms. Now, there's the second one. Now, second one is something very interesting. This is something, have anybody of you done optimization here? Nobody has done optimization? So if I say I give you this kind of a stuff, minimize 3x plus 4y plus 2z such that x plus 2y plus z is more than 2 and x plus y plus z is more than 5. No, that's not good. This is not right. So this is a 5 and maybe so forget this. So this is more than 2 and x, y, z are all bigger than 0. Now, this is an LP, simple LP, right? Can somebody tell me, can you say that what is the value of this LP? How low can you get it?
What do you mean by value?
So this is a minimum, right?
Okay. Okay.
So what is how low can this object be? Can this object be lower than 5? Can this object be lower than 5? This minimum value?
No, we can actually have that, we can equate it greater than 5, right? We can take x plus, we can rewrite this expression as x plus 2x plus 2y plus 2y plus z plus z, and we can group together one thing and we can say that that should be greater than 5 always, right? So basically, sir, the first constraint is inside the equation. That's what I'm saying.
First constraint. Think that this case, right? Right? I mean, I have to
Sir,
add.
just one thing.
Yeah.
The first constant is x plus 2y plus z, right?
Yes.
No, or 3.
No, Z.
Okay.
Yeah. See, the basic idea is that look at this constraint. From here, I have to add 2x plus 2y plus z to get this stuff, right? And since x, y, z are bigger than 0, so that means I have to add something more than 0, which means that this value must be more than this value, which is more than 5. Is this clear?
Yes, sir.
Okay. For what about the rest? Is it fine that this value, the minimum value of this LP, cannot be less than 5?
Yes, sir.
Okay. What about 7? Can the minimum value of this LP be less than 7?
No.
Okay, why?
So essentially, we can add both the constraints and we
Can
would get
add
that.
both the constraint, right? So in fact, I can talk about a slightly different one, right? I can multiply the first constraint with alpha 1. I can multiply the second constant with alpha 2, and so on and so forth. And as long as alpha times the first constraint plus alpha 2 times the second constraint is less than, or maybe alpha times, or maybe let's not talk about this is alpha times first constant or second terms. If I can get you alpha times x plus 2y plus z plus alpha 2 times x plus z, as long as this is less than 3x plus 4y plus 2z. Now, what do I mean by less than? Okay, sorry, I made a mess here. What I mean is that as long as alpha 1x, so rather look at the value of x here, okay, as long as alpha 1 plus alpha 2, alpha 1 plus alpha 2, and alpha 1 plus alpha 2 is less than 3, alpha 2 times alpha 1 plus 0 is less than 4, and alpha 1 plus alpha 2 is less than 4. What can I say? As long as this happens, then the value of the LP is more than 5 times alpha 1 plus 2 times alpha 2. Is this clear?
Yes, sir.
So in other words, if I can construct another one, but this time maximize such that alpha 1 plus alpha 2 is less than equal to 3, 2 times alpha 1 is less than 4, alpha 1 times alpha 2 is less than 4, and alpha 1s to alpha 2 to alpha 3 are just some real numbers. I don't care how much. This quantity is another LP. So if I call this one as LP2 and this is an LP1, do you see that the value of LP1, that LP1 is lower bounded by LP2?
Sir, last alpha 1 plus alpha 2 less than equal to 2.
Oh, 2 it will be, no? Yeah, right. That will be 2, right? Exactly 2. Sorry. Yeah. Right. I have not done anything non-trivial here. It is just trying to do some very stupid math. This is an LP. I wanted to find the minimum of this thing.
Hello.
Lower bound I can get. I wrote,
Hello, sir.
wrote
You
another
are
program
not.
for it. Yeah.
You are not audible in between.
Oh, for how much time?
Like after the you said that it's quite non-trivial, but it's not non-trivial. It's trivial, but after that you are not audible.
Oh, okay. So I don't remember where I told it that. But basically,
That
what I
we are
said,
just doing some stupid math and then
okay, we are doing a stupid math here, right? That I want to lower bound the value of LP1, which means that all I did was that I thought, okay, if I can multiply this equation, first equation by alpha1 and second equation by alpha2, and I add them up, and still individually, coordinate wise, I am less than my destined, my what I want to output, right? Then alpha1 times alpha 5 times alpha1 plus 2 times alpha2 is the lower bound of the whole thing. Okay, which means that, okay, so then what did I do? I did another LP to find out the maximum lower bound I can get. I told it, okay, let alpha1 and alpha2 are p2 variables such that I want to maximize 5 times alpha1 plus 2 times alpha2 such that individual coordinates of these two are less than this. That's all that I told. Is this fine? Hello?
Yes, sir. Is it not the dual problem?
This is the dual problem. And this is the what is known as the dual of the LP. Okay, so basically, if I have a minimization problem, now I have not defined LP for you formally. Okay, so basically, if I define it like this, it's like C is a constant vector, X is the vector that I want to find, minimum C transpose X, such that A dot X is less than B and X's are positive, then you can write a dual of this. Since it is minimum, you can write a maximum. Okay, the maximum will be B transpose Y such that, okay, now this is where I get very confused. I think Y dot A transpose is less than C and Y is a real. This is just a formal of writing what I just did as an example. This was an LP, this was a dual of that LP. This was a max, this is a mean problem, this is a max problem. And all that you can say is that if this is called the primal, this is called the dual, and what you can just say that the primal is always more than the dual. Not only that, do you know what? This is equal. This is one of the biggest and most outstanding results in mathematics. It's called the primality condition or primal dual condition of LP. Now, why am I saying all of these things to you? Because when we want to solve the problem like a vortex cover, which has an LP, I can write the dual of that. That has a meaning. And once you have the dual meaning, if you solve the dual, problem, you get a lower bound on the vertex cover. Okay, so that is a way of handling of the problem. So the second approach, the first approach was to use a relaxed LP. The second approach that I will take out is using primal dual technique. Now this is something that you will learn both in your randomized algorithms course as well as in your, if you do your optimization course there also. Primal dual technique, a very powerful technique, again starting from very basic concepts. But
Sir, I
Yeah.
had two questions.
Yeah.
The first is that the primal duality gap being 0 is only the case for the linear programming.
only for the
not
linear
for
program, yes.
ILPs.
Yeah, not for ILPs.
And the
On-
second thing is, yeah. So the second thing is that this is only possible because of the non-negative constraints in minimum or non-positive.
No, you can do it for
constraints?
anything. I mean, if you are negative constant, you just have to change the signs and all those things.
Okay, but then also it will hold.
Yeah. All
Yeah,
of this.
but all of the variables have to be either non-negative or like some variables being negative and some being positive. Would
Oh, that also can be converted. Okay, so there are some tricks that you
Okay,
which
okay.
you can write every variable as a sum of two variables, both of.
Yes,
of
yes,
them.
I think, yeah, that can be.
Okay, so those things are all. So every LP has a dual. Okay, so this is something that if you guys are interested, it's a very powerful thing. This is studied a lot in not only in computer science, but also in operation research and in various other areas. Now, the third problem that I'm talking about is something slightly different, not through LP, not through ILP or any such thing, but just directly trying to understand the problem. So you remember this vertex cover. What is this vertex cover here? I have a set of graph. I have a graph, and my job is to pick the smallest number of vertices such that every thing is picked, right? Something like that. Now, what happens? I don't know how to solve it. In fact, I should not be able to solve it, right? Exactly, because this is NP complete. But what happens if I find a matching, maximum matching? M. So that means the size of M equals to M. What does it mean? That means in this graph, okay, there are matching of size M. M of them are there. What can we say about the vertex cover?
It has to be larger than M. Like
Okay.
the minimum vertex cover is larger than the maximum.
It has to be larger than M, right? It has to be larger than M, because this vertex cannot handle this edge, or this vertex cannot handle any of the edges. Similarly, this vertex cannot handle any of these edges. So for each of these edges, exactly one or at least one from each of them has to be picked up. Wonderful. Now, what does this meaning by a maximum vertex cover?
The entire vertex.
Not
set.
necessarily, not entire. That's perfect vertex cover. Sorry, and so maximum matching. I meant. What is minimum
Yes.
maximum matching?
So maximum matching is that I cannot extend the matching anymore.
I cannot extend, because if I take a vertex here and the vertex here, oh no, that if there is an edge, then I would be able to pick it up. So in that case, that is not maximum, right? So maximum matching meaning that if I take any other vertex here, and look at all its edges, they are either touching these vertices, right? It cannot be that there is two unmatched vertex and there is an edge between them. That is not possible, right? This is not
Yes.
possible, right? So that means every vertex has edges to this matched vertices, right? And this is what I want. What happens if I choose all of them in my vertex cover? Is this a vertex cover? All matched vertices. Is this a vertex cover?
Yes.
It has to be, right? Because if not, that means there is some edge that is not attached to this set of edges vertices. But then I know that would have been picked up by a maximum edge, maximum vertex matching, right? That's not possible. So I wanted to find vertex cover. Instead of that, I have produced you a vertex cover. I wanted to find the minimum vertex cover. I know the minimum vertex cover is bigger than m. Instead of say, I have given you a vertex cover prime whose size is less than twice m, because this number of matched vertices is how much? Twice m, right? So while I was trying to find a vertex cover of size m, which is what I was trying to get, I can easily give you a vertex cover which is less than twice m. That means in polytime, I can give a vertex cover of size 2 times the optimum. This is also kind of almost magical, right? That yes, this is an NP-complete problem, so I don't know how to solve it exactly, but you will be able to approximate it very well within a factor of 2. Now, this is what is called approximation algorithms. Now, this is a very big area again, extremely big. In fact, this area is so big that it goes into the realms of, it touches complexity theory also. Because now, say I have given you an 2 approximation of vertex cover. Okay, so this is in polytime. In p times, I can find a 2 approximation of vertex cover. Of course, I know the 1 approximation, which is basically the exact approximation. This is NP-complete. A natural question for you is that, okay, can you get me something better than 2? What about 1.5? So can vertex cover be approximated by a factor of 1.5? The actual answer is no. And this goes into the area of called inapproximability. Now, if you ask me what is inapproximability, it basically says that, okay, some problem cannot be approximated beyond this time unless p is equals to np. Or in other words, this basically says that it is NP complete to approximate beyond 2. to approximate beyond 2 for vertex cover. Now, while this algorithm, this statement might seem very innocuous, like, okay, you have proved another anti-completeness problem. What's the big deal? Now, I'm going to throw in words here. This area, if you think a bit harder, you'll understand this is very complicated. This is not at all easy. This area comes from purely from the area called probabilistic checkable of proofs. Of proofs, also known as PCP. Using this concept of PCP, you can try to solve this. So this work ties up with two of India's great works. The probabilistic checkable of proofs was first done by this guy called Madhusudan, and he got the Nevalina Award in 2002. And using something called unique games conjecture, which basically uses a lot of Fourier analysis, Subhash Khod, another Indian, got the Nevalina Award, the topmost award in CS in 2018. So in some sense, so Madhusudan and Subhash Khod, so two big names of Indian CS, got Nevalina Award, the highest award in computer science, for the almost the exact same problem, building up to this thing. Now, of course, I'm leaving out a lot of names. There are other Indians, other non-Indians, a lot of people. There's a people called Hastad, a Swedish mathematician, who basically made this connection between PCP and inapproximability the first time he did it. He's a super big name. Then there's a guy called Sanjeev Arora. He was a big time contributor of this PCP theorem. The Mario Segedi and all. And this whole thing gets tied up with another big name. This is an area that very closely uses coding theory, something that has a very strong bonding with ISI, because one of the first and greatest coding theory persons in the world is the name called R.C. Bose. So anyways, so this area is a humongous area of approximation, inapproximability, and everything that goes in there. So yeah, so the reason I'm telling you all of these things is just to kind of tell you this is just the beginning course of algorithms. As I told you, this will be the last class, which means that I am not going to do anything else, of course. And I just want you guys to, again, just remember this thing, that try to think algorithmically. So this is the only takeaway from this class that I can give you, that instead of trying to think in a greedy and heuristic manner, try to think in a bit more organized, possibly counterintuitive way, namely by recursion, reduction, and by analyzing your solution. Okay, this is just a start. If you are interested in any subject in computer science, this one is there. If you want to continue further in learning more about this advanced topics in algorithms and all, I will be happy to talk to you guys and advise you with the huge and very interesting things that are there here. Just 1 second. Yeah. So yeah, I think I will stop today, and in fact for this course. If you have any doubts, do let me know. Do let the PS know. Yeah.
So last class we did network flow, right? So you asked us to show network flow is NP.
Yes.
So I didn't get the like one side reduction. I didn't get like. So which problem should we use to show that it is equivalent to a network flow?
It is not NP complete. It is in P. I told you P. Network flow is in P, not NP. It is in NP for certain. It is also in P. So you don't expect to prove NP complete.
Okay, got it, sir.
Okay. Hint is write network flow as the pure linear program, not an ILP, but an LP itself. Okay. And once you solve it, reduce it to LP, then you can solve it because LP can be solved.
Yes, sir, got it.
Okay. Now, okay. By the way, I have just proved to you guys that matching and network flows can be done in polynomial time. That is not the end of it. Okay. Of course, you should not take that is the best algorithms and all. There are, because these are very classic algorithms. So there's a lot of work about how to reduce the complexity. Okay. For example, here we just showed that matching can be done with n to the power 5. It can be done in much lower, like n squared, n cube, and so on. Okay. Depending on which, if it is bipartite or not bipartite, and so on. So there are lots and lots of work on finding the best. Similarly, for flow, while it's true that using LP you can solve it in polynomial time, but there are other much more nice ways of proving network flow. Namely, there is the algorithm called Ford-Fulkerson. Again, something that I did not do in this course. I did not have time for it. If you guys are interested, you can take a look at it. Yeah, and actually this ties up with something in discrete math, because there is something called have you heard of cuts? Max flow min cut theorem.
Yeah, min cuts.
Yeah, so the max flow min cut theorem can be written as a special case of, okay, battery is gone. So max flow min cut theorem can be written as a special case of network flow. Yeah, can be solved using or proved using the Ford-Fulkerson method. Okay. So yeah, that's it, I think. Yeah. Yeah, so there are a lot of things I could not do in the course, but yeah, for this exam, please try your exercises. Try to understand the stuff that are done in class, and for people who have done things in class, it should not be too hard to do well in the exam. Okay, so any questions? Hence, I will stop this class for now.
So today's topic is included in the exam.
Yes.
Okay, sir.
Okay. So see you guys.